Hello, hello. Let me know when you can see and hear me, please. Hi. Hello. Say hi when you can see me. Hi, A. Who else do we have? Are you here by yourself? Okay, hey. One-to-one tuition for you. Okay, so everyone, anyone else in the chat, please don't be shy. Say hi. So we're not going to be on here for that long, but we will hopefully do these each week where we just have a quick drop in for you to ask me particular questions. Now, bear in mind, these questions should be A-level questions, okay? So if you're doing your chemistry degrees, the questions will need to be linked to our A-level courses, okay? Lovely. A, absolutely. We can look at naming organic compounds. Hi, Anoma. Hi, hi, hi. So A, what year are you in and which functional groups? Actually, no, just what year are you in? Because then we can look at which compounds we'll focus on naming at the moment. What exam board? So I teach AQA, but I have also taught OCR and EdXL. Okay, so you can ask me any question. And to be fair, most of the exam boards are pretty similar because ultimately they're trying to get you ready for university. Okay, so they want to make sure that you've got a similar level of knowledge. There are small differences, but I'll let you know if it's a difference. Okay. Ooh, 1 year fast track. Wow, that is very exciting. Okay, so let's start with some of the simplest ones, naming organic compounds. Let's start with some displayed formulae and then we can go into skeletal. Okay, unless you have a preference for one or the other to start with. If you're already happy with displayed, you want to go straight to skeletal, let me know. Otherwise, we'll start more straightforward. Okay, lovely. So let's just have something nice and simple like this. Will this be saved? So Colleen, great question. This will be on my channel, so you can come back and watch the live stream. I think, oh, actually, do I know that for a fact? I think so. Okay, but make sure that you are subscribed, okay, so that you will still have access to what's on the channel. Okay, let's draw this. And hi, Colleen. Okay, so in order to name this compound, we would want to start with, of course, the longest carbon chain. Can you tell me how many carbons in the longest carbon chain here? Oh, amazing, Colleen. Great. Glad to hear it. And anyone that's here that's not subscribed, please subscribe. Please like the video. Lovely A5. So if we've got a 5 carbon chain, then we're doing pent. Hi, Mariam. Welcome. Great. So this is actually, I'll shuffle it over a bit so I know I don't run out of space. This is going to be a pent. Now, because we don't have any kind of exciting functional groups like alcohols or carboxylic acids, and all of our carbons are bonded by carbon-carbon single bonds, then this is a saturated hydrocarbon. Sorry, it's not hydrocarbon, saturated organic compound. So it will end in ane, so pentane. But now we need to consider our branches. We have got a chloro group and we've got a methyl group. So this will be either methyl chloro or chloromethyl. Which one would it be? Methyl chloro or chloromethyl? No problem. Hi, Connor. Lovely A, chloromethyl, because we need to put our branches, so our substituents, in alphabetical order. Okay, but we're not done yet. We need to now position where those groups are. So we need to give them numbers based on where they are in the carbon chain. Now, how we choose the numbers, remember, we can number either from left to right or from right to left. We choose the one that's going to give us the smallest number. Okay, so if we numbered from, let's do both examples. If we numbered from left to right, then we can say 1, 2, 3, 4, 5, and then that would give us 3, hang on, 4 chloro, 3 methyl pentane. Or if we numbered from right to left, making this carbon 1, 2, 3, 4, and 5, we get 2 chloro, 3 methyl. Absolutely A. So right to left will be our preferred option here because that gives us our smallest number. So this would be 2 chloro, 3 methyl pentane. Notice that between letters and numbers, we put just a hyphen to separate them. Okay. I'm going to do another one. If anybody wants me to go through something else, ooh, Connor, absolutely, we'll do that next. We'll name a couple more compounds and then we'll go to LCP, Le Chatelier's principle, my bestie. Okay, let's try this one. How mean do I want to be? Actually, not mean. Let's do this. Okay. Lovely. Bear in mind, this is not fully displayed because displayed would mean that every single bond is shown. So actually, to make this a displayed formula, we would make this O and then we draw the bond between the H as well. Okay. Lovely. Mariam, you're getting a head start to your A-level chemistry, so this is really exciting. So again, just as before, we're going to start with our longest carbon chain, which is how many? And therefore, what's our root? How many carbons? What's the root of our name? Lovely. 4, which will make this a bute. Okay, if I start writing behind my head, please let me know. So this is a bute. Let me draw that a bit more clearly. Now, because we have this OH, instead of it just being called butane, instead it's going to be butanol. Okay, notice I've left a gap between the N and the O for a reason. The reason I've left that gap is because just like before, we need to position any group that we have. Okay. Now this alcohol group, this OH, we can decide, is that alcohol group on carbon number 4 or is that alcohol group on carbon number 1? Just like before, we want the smallest possible number. So this would be butan 1-ol. Okay. Now we've got 2 more groups. We've got 2 bromo groups, so 2 bromines. So because we've got 2 of them, we would need to call this dibromo. Okay. If there's only one group, we don't need to say mono, but if there's more than one, then we need to say di or tri or what comes next? Tetra. And again, we need to position those bromines. Where are they? Which carbon? Again, we've already decided that we're numbering from right to left. So our bromos. So Mariam, when we have branches for our halogens, they become halos. So in the same way here, it was chloro, not chlorine. Here it's bromo. If it was iodine, it would be iodo. Okay, absolutely. Anoma, you've got it. So it will be 2,2-dibromo-butan-1-ol. Okay, we have to give both 2's because we have to say where both of those bromines are. Because if the bromine was over on this carbon here, then it would be 2,4-dibromo. Okay, lovely. Should we do one more name? Let's do another one. These aren't equations, these are just naming organic compounds. This first one we would classify as a halo alkane, or depending on what exam board, sometimes they're called halo alkanes, sometimes they're called halogeno alkanes. And then here, what would this be called? Oh gosh, an alcohol, but with a bromo, so halogenol, I don't know. Double bond with oxygen. Yeah, let's do it. Okay. And I'm going to go skeletal now, Mrs. Al-Yassiri. So let's go 1, 2. Actually, no, let me not count out loud because then I'm giving it away. Actually, no, let me not do that. Okay, let's name this. Again, we're following the same principle, right? We want to start with like the root, what's the longest carbon chains that we know if we're giving it, you know, a mether, etc. Lovely A, so 4 carbons. So this is going to be a bute. We only have carbon-carbon single bonds, so you're absolutely right as well. It's going to be a bute and something. Now we need to look at our functional group. We have this carbonyl group, C double bond O. What would we call this functional group? When we've got a C double bond O, so a carbonyl group that's in the middle of our chain, we call this group not an ol. An ol would be OH. A C double bond O, this is called a ketone. So it ends in -one, absolutely. Okay, an acid, Connor, so an acid which would end in oic acid, that looks like this. So a C double bond O still there, but also an OH attached to that same carbon. Okay, so we need both of these for it to be considered an acid. If it's just the C double bond O, then we've got options. The reason I started to draw this lovely diagram up at the top is because if the carbonyl group is in the middle of the chain somewhere, it's a ketone, whereas if the carbonyl group was at the end of the chain, then we would call this an aldehyde instead. Okay, no problem, Mariam. I will see you in our class next week. Tuesday? No, Wednesday. Okay, lovely. So this ends in own. And best practice, we should position that. Now, what number will we use to position this own group, this ketone? Again, we've got 2 options. We can either say 1, 2, 3, 4, lovely, or 1, 2, 3, 4. We want to give that 2, so the smallest possible number. And whatever is at the end of the name will get the smallest possible number. Because now we've got this group here, so a 1 carbon branch. If we have a 1 carbon alkyl branch, so just C's and H's, we would just call that methyl. And that methyl group is on carbon number 3 because we've already identified that this is carbon number 2. So 3-methyl butan 2O. Notice we could have said, in theory, 2-methyl butan 3-one, and that still gives us the same like numbers overall. It's still a 2 and a 3, but why is it this one and not that one? Oh, I'll answer that question in a moment, A. Good question. The reason that we have to give the 2 to the own is because whatever gets the ending typically gets the smaller number, because the ending is typically the higher priority. Okay, so butan 3-methyl butan 2-one and not 2-methyl butan 3-one. We know it's methyl, A, because we've only got one carbon, let me move my little red circle. We only have one carbon attached to this carbon. So this carbon is part of our main chain. So 1, 2, 3, 4. And then we have an extra branch, which if we were to draw out what's actually happening, that's a CH3. Okay. Okay. Should we do one more? A trickier one? And skeletal. Tricky, skeletal, bringing it all together. Yeah. Let's do it. Does anyone have any particular functional groups that they want me to include? Connor, I will definitely answer that question after this next one. Okay, this will be our last naming, and then we'll go to your concentration Le Chatelier's principal question. Okay, lovely. One last difficult one. Ooh, how do I feel about this? Okay, okay, lovely. So let's follow the same principle. We'll start with the root, longest carbon chain. Okay, oh no. So again, we've got 4 carbons, right? So 1, 2, 3, 4. So we're dealing with another butte. Absolutely, Connor. This is your carboxylic acid. Fantastic. So this is a butte. Now, our last couple, those were butanes. But because we've now got a carbon-carbon double bond, this is now going to be absolutely a butene. And because we have a carboxylic acid, it's going to end in oic acid. So butene oic acid to start with. Okay. Now let's position that ene, because that carbon-carbon double bond could have been in another place. So we have to say exactly where it is to identify this particular molecule. Okay. Now, carboxylic acids have got the highest priority out of any group, right? They're so important. So carboxylic acids are always number 1, which means that we don't need to number carboxylic acids. That's number 1 already, okay? Which means that this carbon must be number 2. And because our carbon-carbon double bond starts at carbon number 2, we would call this but-2-ene oic acid to start with. Okay. We also have our chlorine. So that's going to be our prefix chloro. And of course, we have to position that. It's also on carbon 2. So 2-chlorobutenoic acid. Yeah, absolutely, Patrick. So we've got the chlorine in there now. And you tell me, how much have you done on stereoisomers? So EZ isomerism. Because whenever we've got a carbon-carbon, I can't speak, a carbon-carbon double bond, we should always look out for EZ isomerism. That doesn't mean it's always going to be there. Okay, doesn't mean it's always going to be there, but we should look out for it to see if it is there. So for our EZ isomerism, the E, well, it's German. Any German speakers in the chat? The E stands for the German word entgegen. Oh, careful, this does not have cis-trans isomers. It only has EZ isomers. Okay, so the E, okay, lovely. So you can show off to your dad later on and say, oh, entgegen, and the Z is for zusammen. Okay, and the easiest way to remember that is if we have zusammen, well, if we know the word, then we see the word same in the middle. So when we have our carbon-carbon double bond, we've got two groups on either of those carbons. The two highest priority groups can either be on the same side or the same side, or they can be on opposite sides. Okay, stick with me, Ian. And if you haven't done stereoisomerism yet, then this might be quite confusing. But once you've done it, hopefully this will all become clear. Okay, so what we'll do is we'll look at each of our carbons in the carbon-carbon double bond, and we'll look at which group has got the higher priority. So on this carbon here, we have got this methyl group, and we have an invisible hydrogen that we didn't have to draw because it was skeletal. Now, because the methyl group has got, well, the carbon on this methyl group has a higher atomic number than hydrogen, that means that our methyl group is the higher priority. So our higher priority is down here. Let me change my color. Priority. Now, if we look over our next carbon in the carbon-carbon double bond, we have got to choose between chlorine and carbon. Again, which one has a higher atomic number, chlorine or carbon? Well, you can look at your periodic tables that I know you all have in front of you, and you'll see that chlorine has a higher atomic number than carbon, which means that chlorine has the priority out of these two. Okay? Now, because both priority groups are facing in the same direction, so they're both facing down, that means that our priority groups are on the same side. So this would give us the Z stereoisomer, which, to be fair, best practice to put it in brackets. Okay. Again, once you've studied more about EZ isomerism, then maybe we can come back in a future Ask Me Anything and we can focus even more on that. Okay. I'm going to go now to Connor's question about Le Chatelier's principle. Okay. Oh, okay. KNX, if we've got time, we'll come there next, but let's go to our good friend LCP. So Le Chatelier's principle and equilibrium. So the foundation of Le Chatelier's principle is essentially that the position of the equilibrium will shift to oppose any change. So if we make a change to the system, then the equilibrium will shift in whichever direction is going to oppose that change and bring us back to where we were before. Okay, so Connor's question was specifically about concentration. So let's say we've got a chemical reaction. I'm going to make one up with just random letters. Let's say we've got a reaction between A and B, and when those react, that produces C, and that reaction is in equilibrium. Okay. Now, if we change the concentrations of any of these species, the equilibrium will shift to try and reduce that concentration. Okay, so let's say we increase the concentration of A. That means that the equilibrium will want to try to decrease the concentration of A. And the only way to decrease the concentration of A is by the equilibrium shifting to the right, because then the A is going to get used up because it will have to react with B. Okay, so shifts to the right-hand side to decrease. Am I behind my head? Not yet. The concentration of A. Okay, Connor, are you still with me? Let's try one more example. Same equation. This time, if we were to increase the concentration of C, then in order to try and bring that concentration back down again, the equilibrium is going to shift in the direction that uses C up to make more A and B. So the equilibrium will shift to the left-hand side to decrease the concentration of C. Okay, so the equilibrium shifts in whichever direction is going to oppose whatever change it is that we put on it. Okay. Connor, let me know if you are happy with that or if you have any further questions. I'm going to answer A's question super quickly. So yes, I studied chemistry at university. So I studied chemistry at Oxford University. For my A levels, I did biology, chemistry, and maths. Yeah. And then back in my day, we used to do AS as well. Everyone did AS levels in the first year as well. So I did additional AS levels in English literature and French. Okay, lovely A, fantastic choice. I'm not biased at all. Are you looking at doing chemistry at university as well, A? If so, it might be worth coming to a future Ask Me Anything and maybe ask me about, university prep for chemistry. Okay, when we've got more time. Explaining the naming of organic compounds. So KNX, we've looked at a few examples of organic compounds. So I'd recommend maybe re-watching this stream so you see the examples that we did at the beginning, but we didn't see any cyclic alkanes. So let's do two examples. Let's do one with Patrick's question, talking about and ANOMA, so maybe elaborating on stereoisomerism, but then also with a cyclic alkane. So let's do two more examples, and then I've got to go and actually eat my lunch, okay? I hope that you are having your lunch while you're doing some chemistry with me, okay? Okay, nice to see, A. Okay, let's come back to our naming because it is so much fun. Let's have a cyclic alkane. So, actually, I don't like that shape. No offense. That's even worse. Oh my gosh. Okay. Looks a bit like a hat, but that's fine. Okay. And then let's put a branch there. Now, we'll still start in the same way as we did before. We're looking at how many carbons, but this time we're not necessarily looking at a chain. We're just looking at how many carbons do we have within the ring. Ooh, Alan, so I would need more time to prep for proton NMR because I would need a spectrum up on the screen to refer to. But for a future one, we can make a whole session about proton NMR, okay? So here, because we've got a 5-membered ring, this is going to be pent. So more specifically, we would just call this cyclopentane. Now, attached to one of these carbons, we have a 1-carbon branch, okay? 1 carbon is meth, and because it's a branch, that's yl, so this would be called methyl cyclopentane. Now, we don't need to number that methyl, and that's because this has got rotational symmetry. So every single one of these carbons is exactly the same. So whether I drew it like that, or I drew it like this, or I'll do one more example, or like this, all 3 of these are exactly the same. Okay, so I don't necessarily need to call this 1-methyl cyclopentane because there's only one place it could have gone. Good question. So for our A-level courses, it depends. So in year 12, we just have one chemistry course for A-level. And so it's designed towards the AQA specification, but there are students of multiple exam boards in there because in year 12, most of it is really similar. But when we get to year 13, that's when we split the A-level course into 2 exam boards. So we have the AQA course, which is what I teach, and then we have the OCR course, which is what Dav Does Chemistry teaches. Okay, so 1 A-level course in year 12 and then split into 2 in year 13 so that we can make it really specialized and give you the exam prep that's going to get you the best results in your final exams and all the, revision courses. Not Edexcel at the moment, but to be fair, OCR and Edexcel are pretty similar. I'd recommend maybe having a look at your specification compared to OCR and see how well it matches, okay? Because from teaching OCR and Edexcel, I would say those are the two most similar exam boards. So I think it would still be really, really helpful, okay? What will it be called when the methyl branch also has a branch? The methyl branch can't have a branch. It can be an ethyl with a branch. So like this. So here we've got two options. And what would we call this? We can do this in a couple of different ways. We could call this, oh my gosh, what would we call this? Isopropyl cyclopentane or methyl ethyl cyclopentane, because we have an ethyl group, 2 carbons, and then we have a methyl group on the ethyl group. Okay, very unlikely that you'd be asked to name anything like this at A level, because really the better name for this, which is not an IUPAC name, but is one that you would use out in the real world, would be isopropyl, because it's 3 carbons, 1, 2, 3, but not arranged at the end, but arranged in the middle. Okay, so isopropyl or methyl ethyl. Okay, we are just about out of time. I want to do one more example to answer a previous question. For Markovnikov's rule and mechanisms, I think that's going to have to be a future session, okay? But I do want to answer the question that was asked earlier and elaborating a bit more on stereochemistry, okay? So, and I get this question a lot where I do a question on EZ and then somebody goes, isn't it also cis-trans? And the answer is sometimes, okay? Patrick, structure of benzene, that is Googleable. So I'm going to ask you to just search that up, okay? That doesn't need my explanation necessarily. So for EZ, that is based on priority rules, okay? And the priority rules is which has the higher or the greater atomic number. Whereas cis-trans is based on sameness. So is it the same group on the same side or opposite sides? So I'll show you an example where cis-trans and EZ don't necessarily work with each other. So let's have this. Actually, no, this one does work, to be fair. This one does work. Let's do it like this. Okay. So let's first use, because it's easier, let's look at cis-trans rules first. In the chat, actually, can you tell me, would this be the cis isomer or the trans isomer, just by looking at the groups? So looking at sameness, do we have the same groups on the same side or on opposite sides? Let me know. What do you think? Lovely. YZH, excellent. So this would be the cis isomer, because we've got, lovely Anoma, because we've got our two CH3s, which are the same as each other on the same side, okay? But now using EZ rules, where we look at priority, so which has got the higher atomic number, we need to look at it slightly differently. Okay, so we'll look at 1 carbon at a time and we'll ask ourselves which group has the higher priority. So between the chlorine and the carbon, which has the higher atomic number and therefore the higher priority, well, looking at our periodic tables or just from the example that we did earlier, the chloro or the chlorine has got the higher priority. Okay. Now, if we look over at our second carbon in the carbon-carbon double bond, then between the hydrogen and the carbon, again, well, this time rather, the carbon has the higher priority or the higher atomic number, and so the CH3 is our higher priority group. So here, because our high priority groups are on opposite sides, right? So one is pointing up and one is pointing down, as opposed to both of them pointing up or both of them pointing down. This would be the E isomer, the entgegen, the opposite one. Okay, so this is the cis if we're just looking at the sameness, but it's E if we're looking at priorities. Okay, and one more example, if we have something that looks like this, okay, this does not have cis-trans isomers because cis-trans isomerism is based on sameness. And because we don't have a group that is the same across both carbons in our carbon-carbon double bond, we can't assign cis-trans isomers. But because EZ just relies on priority, we can, what word am I looking for? Label it as E or Z. Again, looking at each of our carbons in the carbon-carbon double bond. Between chlorine and bromine, bromine has the higher atomic number. Between hydrogen and carbon, carbon has the higher atomic number. So this would be the E isomer, but does not have cis-trans isomers. Okay. Indeed, KNX. So like I said before, ISO wouldn't be the IUPAC name, which is why they wouldn't ask you to really name a compound like the one we showed before in A level. Okay. Oh, okay. We're already 7 minutes over time. So we're gonna have, should we name? Okay, fine. Let's finish up. Just finishing with the same question, Alan, I like that. We're going to finish by naming this compound and then we have to go, okay? Because we're already almost 10 minutes over, but the aim is to do these at least once a week. So please drop into the next session and I'll try and keep an eye on these questions, but then if you're present, then you can just ask them again, okay? Let's name this compound. Oh, okay. Longest carbon chain. 3, right? We've got 3 carbons, which would make this a prop. And we have a carbon-carbon double bond, which makes this an ene. Now, we don't need to position the ene, and that's because if there's only 3 carbons, then actually, no, should we call it prop 1 ene? We can if we want to, but we don't really have to, okay? So 1, 2, 3 carbons, so propene, and then we'll position our groups, our branches, so our bromo and our chloro. And of course, we'll put those in alphabetical order. So bromo, chloro. And then where are they? By definition, this has to be carbon number 1. Okay, so 1 bromo. Oopsie daisy. 1 bromo, 1 chloro, propene. If we wanted to say prop 1 ene, not the end of the world, but not really necessary. Okay. Okay. Can it be in skeletal form? I'll draw this first one in skeletal. So it would look like, like this. Skeletally. This one would look like that. Okay. So that's how it would look in skeletal form, Patrick. Okay. For now, I am going to thank you for joining. I am going to, oh, lovely, A. I'm going to ask you to please like the video and subscribe to this channel. And there will be more of these coming. The next one is on Tuesday. So Tuesday of next week at 4:30 p.m. Okay. And again, we're going to be doing these weekly. So come and drop into whichever ones work best for you. Amazing. Thank you so much, Ian. Okay, you're very, very welcome. Anoma, Patrick, thank you for joining. Thank you, A. Great work today. I will see you soon. Okay, bye. Oh.